Hello, everyone. My name is Raymundo Arroyave. I'm a professor at Texas A&M, and I want to present an invited talk on the high entropy alloy space. The title of the talk is "The High Entropy Alloy Space is Not as Big as We Think it is." And I recognize that the title is a little bit flashy, but essentially what I'm going to talk about today is about um, the quantification, if you will, of the feasible alloy space in high entropy alloys. This work was done mostly by my former student and now postdoc, Dr. Tanner Kirk. And some of this work, particularly some of the initial frameworks that we developed to explore the high entropy alloy space, were published in this a little bit oldish paper in ACTA in 2018. So this is the outline of my talk. I will proceed with a motivation. I will describe our framework. This is essentially, we frame the problem of alloy design as a search problem, um, and a very specific type of search problem that I will define in a few minutes. I will then discuss some results that we have found in some FCC and BCC high entropy alloys, and then I will provide some summary and conclusions. So, over the past decade, there has been a paradigm shift in the design strategies for high entropy alloys. The traditional alloy design schemes based on main or base constituent elements with some minor additions um, was the traditional way in which metallurgists thought of doing alloy design. In 2004, two different works independently suggested moving towards the center of the composition space with close to equimolar compositions. And in this region, it was argued that uh, uh, it was going to be very likely to observe single phase stable microstructures because of potential configurational entropy gains. And having a single phase microstructure was seen as beneficial. And for many years, looking at equimolar alloys in metallic systems or looking for equimolar alloys in metallic systems was seen as the guiding principle in many, not all, of the efforts to try to explore the high entropy alloy space. Now, it's usually the case that in most cases, like we have learned this in metallurgy for centuries now, true gains in performance are more likely to be found in compositionally and or microstructurally complex alloy spaces. So for the past, maybe 5 years or more, people have been looking at increasingly complex and non-equimolar compositions in the high entropy alloy space. So the question that we set out to answer in this work is whether the high entropy alloy space is really big. And in fact, uh, some people may argue, like we do, for example, that the entropy effect may not be as important because phase stability is ultimately the consequence of competition between phases with different Gibbs energies rather than with different configurational entropies. We may also argue that configurational entropy, the maximum configurational entropy, is very difficult to be attained before the alloy melts to begin with. But a motivation to study the high entropy alloy space has always been the chemical complexity, right? And the principle, the guiding principle here is the more chemically complex an alloy, the more opportunities to potentially observe extraordinary properties. Now, design requirements actually constrain the feasible space. So, even though potentially we have a large space to explore, every time that we impose design constraints based on a particular application that we want to enable using high entropy alloys, it turns out that the feasible space can be significantly reduced. And what we're going to talk about today is, in this talk, is how, by using relatively simple and reasonable constraints, um, we want to see how these constraints actually contribute to the reduction in the feasible space to explore in some example high entropy alloy systems. Okay, so we want to answer the question, how big is the available feasible space? We want to understand potentially whether the feasible space is simply connected. So is there a single island of feasibility in an ocean of infeasibility in the high entropy alloy space? Can we gain insight to the geometry as to the geometry topology of the feasible space? This is, something that we actually haven't finished exploring, but we will provide some visualization of this feasible space. And the other question is, how can we efficiently quantify this feasible space? Okay, so for the past 3 or 4 years, we have looked at this type of alloy search problems as the inverse phase stability problem. And the inverse phase stability is essentially, can be understood in contrast with the forward phase stability. So in our group, we consider the forward phase stability problem as the one in which we use thermodynamic conditions to try to determine the phase stability, or that is phase diagram of a particular alloy. And this phase diagram is predicted by minimization of the Gibbs energy. On the other hand, the inverse phase stability is trying to address the problem of trying to go from a desired phase constitution. So if we want a particular phase to be present under certain, operating conditions, can we actually reverse engineer this requirement in terms of the required thermodynamic conditions to solve this inverse phase stability problem? Now, this is very different from an optimization problem, because here we are talking about potentially just a particular set of phase conditions. So we want a particular phase with a particular range of chemistries, for example. And these type of problems, which are different from optimization, can be understood or can be framed as constraint satisfaction problems. And this is a class of mathematical problems in which the solution consists of finding all the possible sets of design points that satisfy all the constraints that we're throwing into the problem. Okay. So for example, imagine that we're looking at an iron-based alloy and we set some requirements based on our best estimate of the type of microstructures that we think are ideal to solve this particular alloy design problem. And we can potentially say, for example, that we want an austenitic matrix. We want a particular reinforcing phase, in this case, niobium carbide, with at least certain percentage of mass fraction. We want to minimize the volume fraction of detrimental phases. We want to make sure that the material is heat treatable, so we want to be able to erase the microstructure at a particularly reasonable temperature, so then we can do solution anneal and then microstructure design, etc., etc., etc. So we can set up a bunch of potential alloy design conditions, and we can convert that into a set of constraints. And we have developed some frameworks where we use a combination of classification, for example, to try to classify regions of the space as feasible or unfeasible. And we also have combined this machine learning technique with an optimization technique that allows us to grow the boundaries of the feasible region as much as possible to try to capture the total feasible space in an alloy search problem. Okay, so going back to the example that I gave before, this is essentially how the solution looks like. We start exploring the space and we keep going and iterating until we explore the space that satisfies all the design constraints that we have set out to discover. Okay, this is what happens when we say, for example, that we want to identify the single phase solid solution regions in a ternary medium entropy system. So here, just by running our alloy search scheme, we actually immediately find that there are regions, isolated regions. One corresponds to hexagonal closed packed structure and the other one corresponds to BCC. that solve this problem of finding a single phase solid solution in this, three component system. Okay, we can judge whether a particular solution to this problem is good by evaluating the precision and recall. So system or a classifier that has perfect precision is such that every solution identified by the algorithm is actually a true solution. And perfect recall is when all the solutions available were captured by our constraint satisfaction problem algorithm, right? So we typically find that provided we have enough time to sample the space, we can achieve very high precision and recall ratios in our search for alloys in multidimensional problems, okay? So here, for example, I'm going to talk about two very specific cases for search of the high entropy alloys, space. In the first one, we're going to look at phase-centered high entropy alloys. Specifically, we're looking at the Cantor system plus vanadium and aluminum. And we set some constraints. For example, we don't want to look at systems that have more than 10% aluminum. We want alloys that are single phase FCC at 800 Celsius. We want also stable FCC up to the solidus temperature. So we want alloys that go from liquid to solid, and the solid phase is actually FCC. If we want, high temperature applications, we may set minimum solidus temperature to be above 600 Kelvin, which is, roughly what some nickel-based alloys have as solidus temperature. We want a relatively narrow solidification range because we want to ensure that we can, for example, 3D print this alloy. And even though having a small solidification range is not a sufficient condition, it is kind of like a necessary condition. So if we want to avoid problems related to segregation of elements during rapid solidification, it is a sure bet to try to identify alloys that have as narrow solidification range as possible. From experience and from the literature, we know that alloys with less than 100 Kelvin of solidification range or freezing range can be printed. Alloys that have a larger solidification range may sometimes be more difficult to print. So we consider this as an acceptable range or target in our search. And, considering or looking at these different constraints, I'm going to present what we found. So the first thing that we do is to try to map the configurational entropy. And of course, this is not the actual configurational entropy of a system. Rather, this is the maximum attainable configurational entropy for a given composition just by using the entropy of an ideal solution. And a quaternary system corresponds to entropies of 1.4. And what I have here in this plot is a Tisne plot. And essentially what we're doing here is we're trying to project multidimensional space, in this case, a space consisting of 1, 2, 3, 4, 5, 6, 7 elements. So it's a 6-dimensional space into a 2-dimensional projection. So this is a highly nonlinear projection of a high dimensional space, but we can look at these different corners of this hexagon, if you will, as being regions of alloys where we have a particular majority element. So actually in this projection, the different colors correspond to alloys where more than 50% of the constituents are corresponding to the different colors. So here, for example, we have alloys that are on the iron corner of the high entropy alloy space. Here we have manganese, vanadium, aluminum, nickel, etc. Okay. Now this is the configurational entropy. So the alloys at the center tend to have high entropy, and just as a matter of reference, any configurational entropy that is larger than 1.4, so about here, so light green will be a quaternary or more complex alloy. So the vast majority of the alloy space in this visualization corresponds to alloys that are not, binaries or ternaries. Okay. Now, when we start to impose constraints, this is what we find. So about half of the space, more or less, is actually FCC at 800 Celsius. And not surprisingly, this region is centered around nickel and cobalt, and to a certain extent manganese. On the other hand, in the vanadium region, we have, alloys that are mostly BCC, right? So here we have BCC alloys, here we have FCC, and somewhere in between in this high entropy region, or compositionally complex region, we encounter a lot of dual phase microstructures. When we look at the solids, again, not surprisingly, again, we're looking at the solids, but we're also looking at alloys that are FCC. So again, the high solids temperatures correspond to, that are also FCC, correspond to this region in this two-dimensional projection, okay? And again, we're looking at, yes, nickel, cobalt alloys, right? And alloys that tend to be close to the edges, and at the edges is where you have the less entropy and where you're more likely to have unary, binary, and ternary systems, is where you see the highest solidus temperature, okay? So this is important. This means that at least in this FCC system, when we have mixing, mixing tends to lower the solidus temperature a bit. So there's this compromise, right? On the one hand, it seems that simpler alloys tend to have higher melting points than more complex alloys. And again, something that I didn't mention here is that these calculations were done by looking at the thermochemical high entropy alloy 4 database. Okay, if we look at the solidification range, again, there's no surprise. It turns out that less complex alloys have narrower solidification range, and actually the pure corners have probably the narrowest solidification range, as it should be. And the more complex alloys tend to have slightly larger solidification ranges. But if we just focus on the FCC alloys, so alloys that were FCC at 800 Celsius, we see that in general, solidification ranges are not that bad, okay? So they typically are less than 50 Kelvin, as per this diagram. If we, on the other hand, instead of doing an equilibrium solidification, we actually do a shell simulation where we actually take into account the fact that there is infinite diffusivity in the liquid at zero diffusivity in the solid, and we look at the more realistic precipitation sequence, we see that the solidification range actually expands, but there are still some regions in the space where the solidification range tends to be acceptable. And again, these regions tend to be closer and closer to the edges in this two-dimensional projection, okay? Now, when we bring all these things together, including strength, so we're using a strength model that accounts for, complexity in the chemistry. So we're using this strength model, and we're looking at, other quantities, including stacking energy, for example. When we add all these different, quantities, we see that, there is not really a very large region where we see green always, right? So green in this case is good. So we're looking for regions in this space where the color is green for every single one of these different properties that we were looking at, okay? And as you can see, there's always a compromise. Let's ignore for a moment the stacking energy, okay? And let's focus and see what happens when we start progressively adding the effects of including different performance constraints on the feasible alloy space. So, for example, when we say, well, we want alloys that only have 10% aluminum, about half of the alloys in the system have less than 10% aluminum, so that's fine. When, out of these alloys, we then look at alloys that were single phase FCC at 800 Celsius. We see that the total number of alloys is reduced significantly to 7%. So the alloys that are FCC at 800 Celsius that have less than 10% aluminum is just a small fraction of the space. If we consider the solidification range, right, and the solidus temperature, we arrive at 20,000 alloys out of the 400,000 that we have available, and that corresponds to just 4% of the total alloy space. If we consider child solidification, we arrive at the conclusion that the total percentage of alloys in this vast alloy space, so basically out of 1 million samples, alloys that we considered in this very large alloy space, after applying all these different constraints, we find that only about 1% of the total space is feasible, okay? So clearly, again, 1% of a pretty large space is still pretty large, right? So you could spend a lifetime just exploring this 1% of this, particular FCC alloy space. But the truth of the matter is that the space is not as large as one would have thought just by looking at the chemical complexity of this FCC high entropy alloy space, okay? Some interesting results when we look, for example, at the configurational entropy of alloys, and this is basically the distribution of entropies for alloys. If we look at all alloys, we see that they are basically this distribution of entropies is basically the distribution for all the alloys that can be explored in the system, right? And when we look at alloys that pass this phase stability constraint, we're looking at alloys that are FCC at 800 Celsius, we see that the actual entropy is displaced to the left. And what this means essentially in this, a little bit confusing, admittedly, plot is that alloys that satisfy this particular constraint have less entropy or are less complex than the total potential alloy space, okay? So that, and this kind of makes sense. This means that alloys that satisfy a particular constraint are not equally distributed in the total or the entire FCC space that we were trying to explore, okay? If we look at the samples that satisfy all the constraints that we set, or at least constraints related to the solidus, the solidification range, and the phase stability, being FCC at 800 Celsius, what we find is that we find this distribution of compositions, okay? And if you ignore this axis essentially counts the frequency or the relative frequency of these alloys. Here we have the compositions of the different elements. The way we read this histogram is the following. For example, here we see that aluminum is this pink color. We see that no alloy that satisfies all these constraints. So there's, like, in the universe of alloys that satisfy all these constraints, which is basically 1% of the total FCC space, we see that all the alloys have to have less than 10% aluminum, right? There's no alloy that has more than 10% aluminum that also satisfies these constraints. The same thing applies with chromium. We see that there is a distribution peaked at around 5% chromium, but we definitely can say with certainty that in the universe of feasible alloys, there's no alloy that has more than 30 something percent chromium. Okay. On the other hand, we see that in this feasible alloy space, there is a wide range of possible nickel amounts in the solution to this alloy search problem, right? So in essence, by looking at these histogram plots or composition histograms, we can tell more or less what is the chemical signature of the feasible region in this alloy space. Okay. Now we're going to talk about another problem. We're going to switch gears a little bit, and we're going to talk about the refractory BCC alloy space. And the motivation for this is essentially the need to look for increasingly refractory alloys to try to improve the efficiency in, for example, power generation technologies, right? So we know that refractory alloys retain their high strength, the high temperature strength, in a better way than FCC alloys, where we see that there is a decay in the strength as a function of temperature. And actually, this is potentially a big, there's a potential big advantage in moving towards refractory alloys, because we can actually increase the base metal temperature capability in turbine engines, and with that we can increase the efficiency in power generation or in thrust production. Okay. At the same time, because of the fact that refractory alloys tend to be difficult to manufacture, we would like, for example, to find these alloys in a space where they can be printed, right? Because that is perhaps the most effective way of deploying these refractory materials into power, into gas turbine applications. Okay, so this is just a motivation. And here we're basically going to do a similar study to the one that we did before. So we have, the refractory BCC high entropy alloy space. Specifically, we're looking at the tantalum, niobium, aluminum, tungsten, moly, vanadium space. And we are using some hard constraints, such as, relatively low density, much higher solidus temperature. So we're looking at 2000 Celsius at least. We want alloys that are 99% or above BCC at the solidus temperature. We want alloys that are strong, and here we're using the Curtin and Maresca model. So we're looking at the intrinsic strength of the alloy of a particular value at a particular temperature. And we could potentially, for example, use some other type of models for some properties of interest relevant to the performance of these refractory materials. And of course, if we want a material that withstands high temperatures for long times, we want materials that undergo the least creep possible. And as a rule of thumb, that means that we will have to make sure that the operating temperature, for example, 1300 Celsius, was actually about half of the homologous temperature. So that means that we will be looking for alloys that have very high liquidus temperature. Okay, so this is how the this BCC high entropy alloy space looks like. Again, this is a two-dimensional projection of an otherwise higher dimensional space. And here we have tantalum, niobium, aluminum, tungsten, moly, and vanadium. Okay, this is how the density constraint looks like. It turns out that alloys with less than 9%, 9 grams per cubic centimeter are throughout the system mostly, except for obviously where you have tungsten and tantalum. And of course, you are expected to see more of these alloys where you have aluminum. This is the distribution of densities in the alloy space that we find. So there are some really low density alloys. And we also have our target. So about more than half of the alloys actually less than half of the alloys satisfy the 9 grams per cubic centimeter target. And this is the signature of the chemistry, right? So, alloys that are less dense tend to have less tungsten. Alloys that have less density tend to have more aluminum than an average alloy. If we look at the solids, it turns out that this space is pretty good at having a minimum solidus above 2000 Celsius. This is how the histogram of solidus looks like. And in general, most of the alloy space satisfies these constraints, except for the aluminum corner of this high entropy alloy, right? So close to this aluminum corner, we can expect the solidus to be much lower because we have more aluminum. Here we see the composition histogram that is not as heterogeneous as in the previous case, but we see that aluminum alloys tend to be less represented than the rest of the chemistries, because of the fact that the more aluminum you have, the more likely it is that you're going to have low solidus temperature. If we look at the percentage of alloys that have more than 99% BCC, it turns out that, again, most alloys satisfy these constraints. So we're looking at alloys that are, that tend to be mostly BCC throughout the composition range. Okay, and again, this tends to happen when we have, alloys that do not have a lot of aluminum in them. Okay, and when we look at strength, again, we see, something interesting. We see that, most of the alloys about half of the alloys tend to be strong, less strong whenever you have aluminum or even niobium. Okay, now we can also look, for example, at some estimates for the ductile to brittle transition temperature. These are very rough estimates based on a rather uncertain machine learning model, but we were using this model to try to visualize further the performance space in the system. And here we have the liquidus temperature. We were trying to look for alloys that have the highest liquidus temperature possible. And not surprisingly, these alloys tend to be clustered around the tungsten and tantalum corners in this two-dimensional projection. So when we visualize the space and we put all these things together, we can immediately see that there are trade-offs, right? So alloys that are strong, so remember, good, is green here. So alloys that are strong may not be very light, so they are dense, and this is not surprising because this is where the tungsten, corner is. Alloys that are, low density, on the other hand, tend to be weaker, right? It turns out that, alloys that are strong, okay, they also tend to be BCC, so these are strong refractory alloys. And you can tell that by looking at all these constraints. If we put them together at the end, a very small region of the feasible space, if we were to superimpose all these different properties that we're interested in, or performance metrics that we're interested in, when you put them together, we find that the feasible space is actually much more reduced, and I will proceed to quantify it in a minute, right? So in fact, when we look at these particular tight constraints, only a very tiny fraction of the potential space tends to be feasible. And so and again, this is the signature of the the feasible alloy space. So these alloys tend to have niobium, they tend to have vanadium, moly, etc. Okay. When we quantify it, we see that alloys that satisfy the density constraint tend to be 34% of the total space. The solidus temperature above 2000 Celsius corresponds to about 60% of the total feasible space. 65% of the alloys are above 99% BCC phase fraction, and about 50% of the alloys tend to be strong. So when we consider all these different constraints, we see that, however, despite the fact that a lot of these alloys comply with all these different constraints, when we put them together, we find that the intersection of these different constraint boundaries results in only 0.5% of the total space being satisfied. And here we can see why, right? So areas that are green tend to be red or even redder, right? So when we are trying to find feasible regions that satisfy these different constraints, we actually find a very tiny region of the space that is able to meet these performance requirements, okay? We can see what happens, for example, when we relax the constraint. So when we start relaxing the density constraint, we can see that more and more of the space is feasible, right? Not surprisingly, that means that the density constraint is a very active constraint in this search problem. When, on the other hand, perhaps one of the most active constraints is the liquidus constraint. When we apply this constraint, in fact, very, very small, virtually no sample or no alloy with less than 13 grams per cubic centimeter satisfy these constraints. And even if we were to relax the constraint to 14 grams per cubic centimeter, a very tiny percentage of the alloy space is satisfactory. And not surprisingly, again, the region that satisfies this very tight constraint is really close to the tungsten corner of this two-dimensional projection of the refractory high entropy alloy space. When we put everything together, this is what we find, and this is just a a collection of all the different constraints that we were looking at when we were trying to quantify the feasible space in this problem. We actually picked 3 alloys at random, and our colleagues, experimental colleagues, were able to make them and verify that they were 100% BCC, as we had predicted. Of course, we haven't done much of an exploration of this space, but at least in these spot checks, we were very pleased to see that we could at least predict with certain degree of accuracy the phase stability in this alloy system. Okay, so I would like to close my talk. In summary, the search of alloy spaces can be naturally mapped to a constraint satisfaction problem, where your objective is not necessarily to optimize a property, but rather to find all the possible solutions that meet all the possible constraints for a particular application. We have developed algorithms that try to tackle this problem. And what we have found after we apply these algorithms and we use other types of alloy search schemes is that the total alloy space is not as large as we thought it would be. If you have a problem where only 1% of the design space is feasible, that may look kind of disappointing, but actually, on the other hand, I think is quite a good result, because that means that you can focus your attention to only the regions that have some chance of being helpful to meet a particular application requirement. Okay. With that, I would like to thank you for your attention, and I hope to answer questions in the interactive portion of this symposium. Thank you very much.